Right, so here we're going to look into the carboxylic acids, a little bit about their structure and some of the reactions. So you've got the functional group is this carbonyl functional group. Now I'm going to go and have a look at that in the PowerPoint. You'll see the suffix for the carboxylic acids is oic acid, but I want to go and look at this in the PowerPoint as it gives me a little bit more flexibility. Alright, so let me jump across here to the PowerPoint, wrong slide, that one. Okay, so here we go. This is your carboxylic acid functional group. All right, so it's this thing here. Everything inside that dotted box is the carboxyl group. Now we normally summarize that, or in the shorthand formula you'll see it just COOH. But importantly, if they ask you to draw this functional group in an exam, you must show this bond. You don't have to show a R group attached. Remember, R just stands for any carbon-hydrogen chain. But you don't have to show that, but you must show this bond because you must show that this carbon's making 4 bonds, 1, 2, 3, 4. Like I said before, as with any carbonyl, this group is polar. The oxygen is a bit negative, the carbon is a bit positive. That's made worse in this case by the OH over here. So this oxygen is also withdrawing electrons away from the carbon. So this carbon's even more positive. And here you've got a site for possible hydrogen bonding. So you'll see in the notes it actually shows it nice. You can actually have 2 hydrogen bonds set up between every carboxylic acid molecule and the neighboring one. So they've got quite high boiling points and melting points. Let's look at some examples. So here I've shown the delta plus on the carbon. They have got a general formula. I think I've put it on here. Oh, I haven't put the general formula on. Let's see, it'll maybe turn up earlier on. Here's showing the acidic reaction. Now they're all weak acids, all right? I've said it over here, they're all weak acids. What happens is this hydrogen that's on the OH is donated. And so that comes off, goes onto a water molecule, making it H3O+. And you can see here the molecule is left with that hydrogen missing. Because that hydrogen did not take its electrons, so it went off just as a proton, as a H+. That's why the H3O's now become plus. This CH3COO is now minus. And if this was ethanoic acid, and you'd say ethanoic acid because there's 2 carbons, eth, and then this gives you the anoic acid, ethanoic acid, then this would be the ethanoate anion. All acid-base reactions are actually reversible. That's why I've scribbled on here with forwards and backwards arrows. All right. So a couple of examples. That's methanoic acid when you just got that carbon there, and then this here would be a hydrogen. Methanoic acid. There's ethanoic acid and there is propanoic acid. Now the old-fashioned name for ethanoic acid is acetic acid, and you probably do well to remember that. Why don't you stop the PowerPoint here and go and try and draw those 3 out, draw their full structural formulas out. And you can see the structure of the acidic section of the molecule, the carboxylic acid group here. Go and try and draw those 3 out quickly, the full structural formula. Stop the video. And now for those of you that have actually done that and come back, I'll carry on and hopefully we'll see that either here or on the next slide. Okay, yeah, go and name the anions as well. I've done one for you here. Go and name the other anions also. Alright, stop video. Okay. Right, you've done that. You've come back now and restarted the video. Lovely. Okay, so this slide is just showing you something slightly different. Is that they don't have the same molecular formula. I'm not sure what I was trying to show on that slide. Sorry, let's let it run. That's ethanoic acid and that's propanoic acid. And they don't have the same molecular formula. Yeah, well, it makes sense they wouldn't have because they've got different numbers of carbons. So I'm not sure what I'm trying to show there, to be honest. Anyway, let's move across. So here's methanoic acid, and here I'm showing the formation of the methanoate anion. I didn't ask you to do this whole thing, but I did ask you to draw the 2 structures. That's a methanoate anion, and there's the hydrogen that came off. The old-fashioned name for methanoic acid is formic acid. You might want to remember that as well. So because they're weak acids, you know, obviously this equilibrium lies to the left. And this would be ethanoic acid, and that's the ethanoate anion, and then I've drawn the full structural formula using ChemSketch. Now, the only real reaction we're going to do of carboxylic acids, apart from this acidic reaction. And please remember, if you were reacting this, for example, with a base, sodium hydroxide maybe, then this would form sodium methanoate. Or this one would form, say you're reacting this with potassium hydroxide. Potassium hydroxide is a base. This would then form potassium ethanoate, because this is your anion. Okay, and the potassium ion would locate itself here, or would be attracted to that bit. Right, so the only reaction we're going to do regarding, other reaction we're going to do regarding carboxylic acids is the formation of esters. Now this actually is a little bit complicated, so you need to watch carefully. And we'll do this and then we'll jump back to the notes. So just in general here, the carboxylic acid will react with an alcohol and they make an ester. And this is what we call esterification. That's the reaction we're referring to. They also make water. So that's the general reaction for a carboxylic acid plus an alcohol. Now you use a hydrogen ion catalyst, so we normally use concentrated sulfuric acid, and then we warm it just slightly. You just throw it into some gently warmed water. Here's a more general sort of example, another general example, because it's R and R. Remember, those are just carbon-hydrogen chains. So this could stand for any carboxylic acid group, and this is any alcohol. And what happens is the OH and the H from the alcohol go and join and make a compound like this, which has got the acid bit joined to the alcohol bit through what I call a bridging oxygen. And where you see this functional group, where you see a carbonyl attached to an oxygen attached to another carbon hydrogen group here, that is your ester functional group. Okay. Now don't worry about exactly which this oxygen is. This example seems to show the oxygen coming from the alcohol. And I must be honest, when I have researched this, that's what I found, but that doesn't make sense to me, because I would have always thought it would have been this oxygen, because this hydrogen comes off much more readily. Anyway, you don't really need to know it in that much detail. You just need to know that this is the functional group of the ester formed. And you must be able to do it for specific examples. So, here's methanoic acid, 1 carbon, methanol, 1 carbon. So what happens, this and that hydrogen go and form water. And then over here we get methyl methanoate. So the alcohol bit just comes and jumps on here. And there's your ester linkage. Now the naming we're going to go through in a bit more detail in a minute. In this case it's easy because they were both meth. But if you have slightly different carboxylic acid to alcohol, so for example in this one we've got ethanol, 2 carbons and an OH, ethanol. This water, by the way, comes from there. It just was written too big. PowerPoint seems to be resizing this thing every time I open it. And this is propanoic acid, 1, 2, 3 carbons. So propanoic acid and ethanol again give you an ester, and this is the ester grouping in the middle. That's the carbon double bond to oxygen, and there over there is your bridging oxygen. But remember, this bit came from the alcohol, which was ethanol. Now in the name you put the alcohol bit first, so it's ethyl propanoate, because this bit came from propanoic acid, ethyl propanoate. So you put the alcohol bit of the name first. So I tend to say this, it sounds a bit lumpy, but I say alcohol acid anoate. That just helps me remember which one goes where. Right, that's the same slide again, I think. So we'll just move. Now here I try to make a little animation to kind of show you this thing working. On the left here we've got a carboxylic acid. This is your ethanoic acid. And here we've got propanol. Now stop the video if you want to, and go and just to see if you can work out the structure of the ester that's going to be formed. Just stop the video, go and see if you can work out the structure of the ester. Don't look at the answer, which is already on the PowerPoint. If you can work it out for yourself, then you're doing pretty well. And see if you can work out the name as well. Alright, for those of you who stopped it and did it, and have now come back, I'm going to carry on. Like I said, the carboxylic acid breaks up, and the alcohol breaks up. And the alcohol's oxygen goes and forms a bridging bond onto the old carboxylic acid. So that should be the structure of the ester that you came up with. Okay, just show you that again. The carboxylic acid breaks up and the alcohol breaks up. Now, that's what they were originally. So what was this? This was ethanoic acid, and this was propanol. So what's the name going to be? Alcohol acid anoate. propyl ethanoate. Okay, is going to be, so there's your ethanoic acid and your propanol, so it's going to be propyl ethanoate. Propyl ethanoate, and the name is written as 2 words, and then of course we've got the water formed as well. All right, so that's just a little example. That is the structure of methyl propanoate. What I just want to show you here is that obviously you can flip this molecule around. Here I've just flipped it 180 degrees. These two are exactly the same molecule. If you can see here, the propanoate is on the right in this one. The propanoate bit came from there. 3 carbons here. Here's 3 carbons and the propanoate bit is on the left, but it's exactly the same molecule. Okay, and don't forget to name that correctly. You must look at which way this bond is facing, kind of thing. So when you look at this, if you were writing this in a shorthand, you would start and you'd say, right, CH3, then you got your bridging oxygen, O. Then you got a CO, well that must be the carbonyl group. Then you got a CH2 and then the CH3. If you were writing a condensed formula from this side, you'd write the CH3 first, then the CH2, then the CO, then your bridging oxygen, and then the CH3. So these two formulas might look slightly different, but actually they are exactly the same. If you read them from left to right or right to left, they're exactly the same thing. So both of those would be just methyl propanoate. Methyl propanoate. Okay. So naming of esters here, I'm just trying to make this simple. If this actually makes it more complicated, then please forgive me. Acid plus alcohol makes ester plus water. So I've said it's alcoholyl acid anoate. That's how you make the name. And so for these two, what have we got here? We've got ethanol and propanoate. So it's going to be ethanol and propanoic acid, ethyl propanoate. Right, acid catalyst, ethyl propanoic acid. Right, if you had methanoic acid and methanol, obviously methyl methanoate. That's fairly straightforward. Okay, you need to know a little bit about reactions of esters. The only thing you need to know really is esters can be reformed back into the original product. So the reaction is reversible. I haven't shown it here, but this reaction can actually go backwards. And it goes backwards. If we need acid alkali to cause it, then it'll go backwards in alkaline medium, but it actually can take place in acid medium as well. Usually a hot alkaline solution. And then the ester is what we call hydrolyzed because it reacts with water back to alcohol, and because it's in alkaline solution, it doesn't form the carboxylic acid, it forms the sodium salt of the acid if you use sodium hydroxide. And there's a couple of examples, and this reaction comes in to its own in the making of soap, because you can take long chain natural occurring esters which occur in animal fats and some vegetable fats as well, and you can hydrolyze them in alkaline solution. That's why you may have heard in old days everybody used to have sodium hydroxide in the Victorian era in their kitchens, because they used to make soap, and you sodium hydroxide with the fat that comes from animals or from vegetables, and you can actually make soaps. So these sodium compounds, these sodium ethanoates, so well, not ethanoate, you need a longer chain, would in fact be soaps. All right, if you wanted to get the carboxylic acid, you could just put a concentrated acid back in the solution, and then you'd get the carboxylic acid again. Okay, what are esters used for? Well, they're actually really nice compounds. We got a great pack to do at school when we do these. They're nicely smelling. They smell very nicely. You'll see we're going to make a whole bunch of stuff. Most of them, a lot of them smell, they're very good solvents, so a lot of them smell like things you've used before, glues, paints and stuff like that. But some of them got very nice smells. We can make you know, pear drops and menthol smells and all sorts. They can also be used to make plastic a bit more plasticky, a bit more soft, and since they're generally not toxic, they can be used in kids' toys and things like that. So that's the uses of esters, and then here's the ones I spoke about: fats and oils, known as triglycerides. So they're triesters. They long chain carboxylic acid esters, and made from long chain carboxylic acids and propane, which is 1,2,3 propane and 1,2,3 triol, otherwise known as glycerol. On hydrolysis, then you can make soaps. And so this is an example. There's your triester. You've got 3 ester groupings in this thing, and that was made from a very long chain carboxylic acid, and 1,2,3 propane 1,2,3 trial or glycerol. Give you this ester, treat it with sodium hydroxide, and you get glycerol, and you get sodium stearate, which is soap, a very basic soap. So that's another reaction you just need to be aware of. I've got some examples here. So again, time to stop the video and go and see if you can try and do these. Write the full structural formula of each of these, and then name the ester and write the full structure of the ester. So give yourself, I don't know, you've got 10-15 minutes, 5 examples. Shouldn't take you longer than about a minute or 2 each. Stop the video and then come back here and check your answers. Okay, I'm not going to wait for you. I'm going to assume that you've done that. You're now back, and we can just jump through the answers. So there's methyl propanoate for the first one, methyl methanoate for the second one, propyl butanoate, etc. I don't want to go through each one of those. It probably would take a bit long, and I've been through some of the others in quite a bit of detail. If any of these you can't get or you're not happy with, I know the slide's not the neatest thing in the entire universe. I have tried and drawn the structures here of the actual esters. Then you can send me a message on Teams or email or ask your teacher, and I'm sure they'll be able to sort it out for you. If I've made any mistakes, they've probably been picked up at this time by classes that I've worked with, but if not, just let me know. So here's some more ester questions. These are a little bit more tricky. I've given you the ester, and I'm asking you to go and tell me what was the acid and the alcohol that was used. And there's no other possibilities. There can only be one thing. So you must go and build up the ester and the alcohol from these. Again, stop the video, have a go at them, and then come back. Right, so we know about 12 minutes or so. It should have taken you 12 minutes maximum. I'm going to just put these up quickly. I'll go through the first one because these are a little bit different to the other one. So obviously if you had ethanoic acid and you made methyl ethanoate, the ethanoate bit comes from the acid, so the other bit must have come from the alcohol. So in other words, it must have been methanol. Right, methanol, that's its structure. And then ethanoic acid, you know, probably know its structure. Methyl ethanoate, I think the structure will come up in a minute. So here's the other examples. Propanoic acid, propanol, sorry, this should be propan-1-ol, by the way, because you can have propan-2-ol, butanoic acid, etc., etc., etc. There they are. And there is the structure of that ester. I've combined sort of abbreviated structure and full structural formula. There's the full structural form of that one. This is methyl ethanoate, which is actually this one as well. Methyl ethanoate. Okay, I think that takes us to the end of it. So what I'm going to do here now is just going to jump out of there and go back to the notes quickly and see that we've covered everything in the notes. Maybe make this a little bit bigger and just jump down. I'm nearly finished. I'm not sure how long we'll be going for. So reactions of carboxylic acids, you can see the main one is esterification. Yeah, okay, I didn't mention that it was a condensation reaction. That is when two larger molecules are joined with the elimination of a smaller molecule. Okay, fine. Yeah, ester and water formed, reaction conditions, mixed with an alcohol, concentrated sulfuric acid. Yeah, we mentioned all that. Mixture is warm generally, nice example. There's the example of a name. The alcohol gives you the YL, and the carboxylic acid gives you the anoate. Right, that's what I said. Industry, flavors, fragrances, all that kind of stuff, sweet smelling, these you must just learn. Food, we mentioned all of those. Solvents, glue manufacture, etc. So that's all there, nice smells. And that's it. The notes don't have much on it at all. Right, really hope that helps you. And I think that's just done for now. So let me just see if I can switch this thing off properly. There we